Everybody. So this video is coming after a couple of videos about finding the area under curves of functions, meaning the area between the x-axis and the graph of the function over some interval of x values. We're diverting from that idea for a moment to look at a powerful piece of notation, something called sigma notation, that we're going to use quite often in the next few videos. This is a notation that shows up all over the place, and one of the immediate consequences is it allows us to compactly write some of these ideas that we've been writing down. But more importantly, I think having good notation really lets your intuition guide you a lot more than when notation becomes cumbersome. It's really kind of hard to look at something and decide, glean some meaning from it. Like all notations, it's going to seem, or maybe most notations, it's probably going to seem more complicated in the beginning, and its value will emerge over time. And there's no way to see that value unless you start writing it and reading it and using it so that it becomes part of your mathematical language. Okay, so we'll do a few exercises in this notation. This is maybe your first pass at sigma notation. Maybe you've seen it before. You will certainly see it again as you proceed in your math and or science career. And then we'll, in some other videos, use it to go back to that area problem. So what is sigma notation? Let's say we have a list of numbers, and we'll write them as A's with subscripts, just meaning I have an order to these numbers, right? A sub m is the first one, A sub m plus 1 is the second one, A sub m plus 2 is the third one. We keep going up until the top one that we'll call A sub n. So these are real numbers. And m, n are integers with m less than or equal to n, right? Typically, they're going to be non-negative integers. So we often will start with m is 0 or 1 and count up to some number, but you don't have to. M can be some other integer, and we can count, from 5 to 15 or something. And we're also allowing here for a list of a single number, right? If m and n are the same, this is a list that's just got one single number in it. Okay, so we start with that. Then, and here's our new symbol. We're going to write this. This is the Greek letter sigma, capital sigma. That's I equals m on the bottom to n. That's how we say this. We'll say A sub I. So the way we say this is, one way to say this is the sum from I equals m to n of A sub I. Meaning, we take that list of numbers and we add them up. Oops. M plus 1, A sub m plus 2, and on up to A sub n. Okay? So we're starting with a list, and then we add up that list. That's what sigma notation does. So remember, in this construction, m and n are numbers. They're going to be fixed. Anytime you write our sigma notation, we have limits to this sum, meaning like where we start and where we finish. I is changing. So what we see in this piece right here, A sub I, this is like the general form for each I. And then we go through each value of I and we add those all together. Okay? We sometimes call, or we do call, this list of numbers a finite sequence. And then this is a finite sum, which just adds up the terms of a sequence. Later on, you'll probably experience some work with infinite sequences and sums, in which we use the same or very similar notation. But that's a whole other thing. We don't need to go there yet. Okay, let's do some examples. So let's suppose, right? Let's suppose I have a class with 3 students whose last names are Abbott, Kuan, and Yenso. Let's say I give an exam where their score on the exam is 30, 39, 33. Maybe it's a 40-point exam. right? I could let S sub I equal the ith student's score, right? So here I'm implying there's an order, and I'll just say the order is alphabetical. So the ith student means the first student is S sub 1, is Abbott. Let's just write this. This would be S sub 1, this would be S sub 2, and this would be S sub 3, right? S sub I is the ith student score. So the S sub 3 is the third student score. S sub 2 is the second. S sub 1 is the first. So then if I wrote I equals 1 to 3, the sum of I equals 1 to 3 of S sub I, what I'm telling you to do is we're gonna take this form S sub I and write it for each value of I. S sub 1, right, starting at I equals 1, that's what the bottom tells us. S sub 2, S sub 3, and then of course we know what these are, 30 plus 39 plus 33, which gives us 102. Right, so the sum I equals 1 to 3 of S sub I is 102. Okay, so that's what this notation does. And this gives us nice ways to write things like if I wanted the average score, sometimes we note that as S bar, right? How do I figure out the average? Well, I add up all the scores. I already know how to write this, S sub I, and I divide by how many scores there are. Right, so we can use this notation as part of other constructions. This, of course, would be 102 out of 3, or 34. Right. Now, this is a good example where this notation is not all that useful. With 3 scores, it's just as easy to write adding them up. But if I had 50 students, or if I was developing some mathematics with some long string of data, it's much, much easier to write out this little summation than it is to write lists of huge numbers added together. Not lists of huge numbers, huge lists of numbers, which may be huge numbers. Okay, more typically for us, instead of having this kind of list of given values for each S sub I, we might have a form. What I mean by that is I might write something like I equals 1 to 5 of I squared. Right, so now these are all of my A sub I's. The first one, again, this is the general form. I'm going to write this general form for each value of I, starting at 1, ending at 5, and then add them up. So at 1, I squared, 2 squared, when I equals 2, when I equals 3, we get 3 squared, when I equals 4, we get 4 squared, when I equals 5, we get 5 squared, or 55, okay? Let's do an example where we don't go all the way from 1. We can start at 3, say, and go to 5 of I squared. So now we'd be doing 3 squared plus 4 squared plus 5 squared, which gives us 50, right? So there's an example of summation notation, right? Again, it's not entirely clear that this is useful because I'm doing small examples, but for instance, if you wanted to represent the sum of the first 50 squared numbers, it would be much more difficult to write it out, right? This is no longer equivalent to that, but this compact summation is a much nicer way to write it. Okay, let's do a couple of other examples, and we'll develop a couple of rules about summation notation. For instance, if I take I equals 1 to 5, and I put a 1 here, well, remember what I said. This is the general form, and we just change the I for each value of I. Well, 1 doesn't have I in it, which means when I equals 1, 1 still equals 1. When I equals 2, it's still a 1. When I equals 3, it's still a 1. When I equals 4, it's still a 1. When I equals 5, it's still a 1. So this is just saying add up the number 1 5 times, which gives me 5. More generally, we could say if we add up the first If we go from I equals 1 to n of the number 1, we're going to add up 1 n times, and we'll just get n. Okay. So this still might seem a little silly, and it's hard to express how important this is, but I'll try to give you a little bit of a hint. As we move forward, we're going to be doing some computations with these sums, and it's not that we want to write down, add up the number 1 n times. It's that that emerges, and we can sort of pull that out as an n, for instance, right? And so when you're doing a bunch of work, we can, these are kind of simplification tools that we'll be using. Okay. Here's another one. Suppose we had I equals 1 to n of any constant. So c is just representing some real number. Well, this, of course, is going to be c plus c plus c. And you add up c n times, you get n times c. Okay, so another little simplification rule. Let's go even more general. If I were to say I equals 1, actually it can be m to n of c times a sub I, right? C again is just a real number. Well, what does this mean? This means take this real number, multiply it by a sub m, take this real number, multiply it by a sub m plus 1, take this real number, add it times a sub m times a sub m plus 2, until you get to c times a sub n. But of course, this is addition. We know about the distributive property. We can factor that c from all of these terms. But notice this thing in the parentheses. This is, in fact, the definition we started with at the very beginning. This is just c times the sum of I equals m to n of a sub I. In other words, constants, if you multiply the terms of your sum by a constant, you can slide that sum out front. It's just the distributive property, right? There's no big trick to this for why that works, other than what you already know about how addition behaves, right? So that's a nice manipulation that we'll take advantage of down the line. Let's do a couple of other ones. I think we have enough space for this. No, let's actually create some more space. So let me clear what we have so far. Let's see. Let's take, let's look at the sum I equals m to n of a sub I plus b sub I, right? So suppose I have 2 different terms, okay? Well, what does this mean? Well, I take a sub 1 plus b sub 1 plus a sub 2 plus b sub 2. Oops, not 1 and 2, it's m. And sorry, I was starting at 1 instead of m. A sub m plus 1, b sub m plus 1. And we keep going up until we get to a sub n plus b sub n, right? Well, if we use the rules of addition, I can rewrite this as a sub m plus a sub m plus 1, right? I'm just reordering addition, which we know is possible, and then I can list all of the b terms up to n. But this here, right, is just the definition of the sum from I equals m to n of a sub I. And this here is just the definition of the term of the sum I equals m to n of b sub I. Okay. And also notice, so what this is telling us is that we can split or distribute this summation notation over addition. And in fact, if you look closely, nothing I did depended on the fact that I was adding in here. This could all oh, that was supposed to be a plus there. This could all be minuses in here. These would all then be minuses right here. Okay, so it works for addition and subtraction to split it up. It distributes over both of those like that. All right, let's do one more. Well, we're going to do a few more things. Let's go in the other direction, meaning instead of starting with summation, sometimes we're going to want to go backwards, where we have a list of things added up that we want to write in summation notation. And it's a little bit of an art form. You'll have to kind of poke at something to discern the pattern, but I want to show you a couple of standard patterns that you want to put into your tool belt to help. So for instance, 2 plus 4 plus 6 plus 8 plus 10, right? It might be pretty clear what's happening here, right? At each, we're listing the even numbers and adding them up. If I want to list them using my summation notation, let's try a different index. Let's say k equals 1 to 5. It's just 2k, right? When k equals 1, we get 2. When k equals 2, we get 4. 3, we get 6. 4, we get 8, and so on. What about the odd numbers? Well, this is a nice little trick, right? We can use almost the same thing. We can just go to each of the even numbers as we did above, but then subtract 1, right? So you get the same thing you got in the first line, except for each of these you subtract 1, which is what we have right there. Let's do one more example like this, and then we'll apply this to our area problem. Here's one that's a little more complicated. Let's say I have this sequence, this sum, excuse me, 1 minus 3 plus 9 minus 27 plus 81. Okay? I want to write this as a sum. Okay? The first thing I notice is that there's a couple different things going on. First of all, the sign is changing. It's going negative, positive, negative, positive. And it also looks like we're increasing by a factor of 3 each time. I want to think about these two things differently, or separately, I should say. In other words, there's a times -1 times -1 in each of these steps, right? So I've got two different things going on. So let's start with the times 3. Right? Well, I want to add a factor of 3 for each term. What helps me count factors? That's exponents. In other words, right? Every time, so I'm using k as my index, every time k increases, I add a factor of k, of 3, right? Where do I start? Well, how many factors of k is 1? That's 0, right? 3 to the 0 is 1. 3 to 1 is 3. 3 squared is 9. 3 to the third is 27. 3 to the fourth is 81. Okay. Now I've got to deal with that -1. Just give myself a little more space here. So I want to do kind of the same thing. I want a factor of -1 each time k increases. And it looks like this will work. Right? -1, when k equals 0, that's a +1. When k equals 1, it's a -1. When k equals 2, it's positive. When k equals 3, it's negative. So we're going to get the right sequence of negatives and positives, right? Which we could simplify this and write it as k equals 0. Oh, I forgot to say when to stop. It's going to go up to 4. I could simplify this as -3 to the k. That will also work. Okay. Okay. There's a lot more to be done with sigma notation, but we'll have plenty of opportunities along the way to work on it in some future videos as we add some complication to our process. But let's do 2 quick things before we go. Let's attach this to the area problem. One of the things we had written last time was the following. the area A between the graph of the continuous function f of x and the x-axis from x equals a to x equals b is, and we wrote a equals the limit as n goes to infinity of, we had f of x sub 1 delta x plus f of x sub 2 delta x on up to f of x sub n delta x, right? Where in the example we did x sub 1, x sub 2, x sub 3, those were the right endpoints of each of our intervals. But in reality, they could be any point in the intervals. Sometimes people notate this by putting a little star here. This just means x1 star is any point in the first interval. x2 star is any point in the second interval. xn star is any point in the nth interval. Well, with the summation notation now, we can write this in a much more compact way. The limit as n goes to infinity of the sum I equals 1 to n of f of x sub I star delta x. And this is what we can take as our definition of the area, right? And at this point, all I've done is compact the notation, which might not seem like the most important thing, but we'll see as we move down the road, it actually really, really will serve us well. Okay, so let's finish by writing out the area under some curve using, as a limit using this summation notation. So clear all that. Let's move this over. We'll keep it up while we do our work. And let's take a look at, let's take a look at, let's express the area under f of x equals the natural log of x from 1 to 5 as a limit with summation notation. Okay, so this is a good time to remember what our little setup is. All right, so let's draw a picture of what we're talking about here. I'm going to put in an x-axis. I'm going to, we'll draw the y-axis. Okay, we're looking at this graph from x equals 1. Let's put that right here to 5, somewhere out there. And if you remember what natural log looks like, it's got an asymptote at 0 going down to negative infinity. It goes right through one, 0, and this would be the point 5 natural log of 5. Okay. So the area we're talking about here is between 1 and 5 and between this graph and the x-axis, which is all of this area. Okay, so how did we do this? Well, the first thing we did was we imagined chopping up this interval into little pieces, right? So if we have n is the number of sub-intervals, right? Then delta x is the width of these. Well, it's, remember, the length of the total interval divided by the number of pieces we chop it into. So in this case, that's 5 minus 1 over n, or 4 over n. Then remember, we labeled all these. This is x naught, x1, x2, dot, 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 up to x sub n. And we had a little formula for this. We said x sub I I'm going to do right endpoints. That's the one we've been doing. I'm going to mostly stick with this. X sub I is equal to, you take the value of x naught, which we also called a, which in this case is 1, plus I times delta x, which in this case is 4 over n, right? In other words, you're just saying, if you start at the value 1 and you want to go, let's say, to I3, you just move over by the change in x 3 times. So you would go 1, 2, 3, and end up at I3. If you wanted to get to x10, you move over 10 more times and get out to x of 10. Each time, you're jumping over by that width, that delta x, which in this case is 4 over n. So we're trying to remember, write something using this formula. I've now got my delta x. I've also got x sub I, right? X sub I star is any point in the interval, and I'm choosing the endpoint. So that means the area we're talking about is going to be the limit as n goes to infinity, the sum, I equals 1 to n, of f of x sub I delta x. Let's write this out now. This is going to be the limit as n goes to infinity, the sum I equals 1 to n of f of, well, what is x sub I? It's 1 plus, I'm going to simplify this fraction a little bit, just write it as 4i over n, times delta x, which is 4 over n. And let's go one more step. The limit as n goes to infinity, I equals 1 to n. F of 1 plus 4i over n, well, f is the natural log of 1 plus 4i over n times 4 over n. All right, so this whole thing is in the summation. Okay. Now, if we want to, there's one more step we could take. This number 4 over n is a constant as far as the summation is concerned, right? N is its upper limit. The sum stops at n, so n is some number. I can slide this out of the constant, so I could write this whole thing as 4 over n times the sum of I equals 1 to n, natural log 1 plus 4i over n. Okay, now I can't slip it any further because this limit is in regards to n, and so it's not a constant in regards to the limit. But as far as the sum is concerned, n is its maximum value, for its index. Okay, and this is an expression of the area under the curve as drawn here, right? Now this is a difficult limit to take. We're going to have to work pretty hard in some later videos to figure out how to get at this limit. We're going to kind of roundabout ourselves into getting that limit. But we will be able to do that, though it's going to take us quite a while to get to natural log areas. Those are a little bit difficult. But right now, we already have an expression that gives us at least a mathematical definition of what that area is. And if this was a problem you really needed to compute, you can certainly compute this or get a reasonable approximation to this using a computer, right? You can program in summations into most programs and let this do it for the first 500 terms and see what, if it starts to approach a certain number, right? This is a way to approximate these kind of areas. But more on that later. That's it for this one. Thanks, everybody. I will see you next time.